Good morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation, and we are continuing with our module 8, that is DER Integrated Distribution Network Fault Analysis and Protection. So, today we will see the fault write through operation of the DERs. That means till then we are saying that okay, if there is fault you just disconnect the DERs or any faulted section from the healthy section. But actually for distributed energy resources, you can run the distributed energy resources for a few certain limit if it also incurs a faulted condition. There is a standard, there is a time limit for it. So, if you run that and within that time if the fault is cleared, so your system is DER will continue its operation. So, we will see how we can do it. So, the fault write through ensures that DER units remain connected during short term grid disturbances without tripping offline unnecessarily. That means, because connecting a DER with the line and synchronize them, the inverters and everything with the line is a difficult process, it is stringent process, it is not a very easy process. Anything making it synchronized with the grid takes a longer time. So, if it is a very short transient fault and if that fault clears within a very short time period, let us say within one cycle it removed. So, at that time unnecessarily if you discard or if you disconnect your DERs, so then again you have to take that effort that you have to make it online or connect it online. So, the FRT or the fault write through capability of the DERs that ensure that it will work for certain time span. So, maintaining DER operation during faults helps stabilize voltage and frequency during system wide disturbances, because DERs not only give you the active power, if you are inverters then you can give even reactive power supply. So, that will be boosting your voltage, that will help to recover from the faulted condition. So, if you are boosting that voltage, that means your fault current will reduce. So, it is easy to remove the fault. So, other than disconnecting the DERs, that will help, if you keep the DERs online, that will help you to recover from the faulted section. Grid codes require DERs to tolerate voltage sags and support the network through reactive power injection. Inverter based and DFIG based systems must implement specific fault write through strategies to meet regulatory compliances. So, there are some grid codes, there are some standards, you cannot make it online like connect it for at the fault for a very long time, then that will hamper the system. So, FRT improves overall system resilience by preventing loss of distributed generation under faulted condition. So, what is the importance of FRT or fault write through in high DER grids, when you have a very high penetration of distributed energy resources in the grid? High DER penetration reduces available fault current, making grid recovery after faults more difficult. Okay? That means, we have seen before as well that if you have DERs, that will if that is a synchronous type DER, that will give you a huge amount of fault current. Okay? So, that will enhance the fault current amplitude. But tripping large number of DERs during faults can cause cascading failures and blackout risk. That means, if you cut down the DERs, all the DERs together, so that will cause the cascading failure, because DERs, I told, DERs is not only giving you the active power, it also gives you the reactive power. So, you will lose all those reactive power suddenly and your voltage will drop again, and that will enhance your fault current from the main grid. So, then that will be difficult to then manage. So, that will lead to a cascading failure. FRT requirements prevent mass disconnection of renewable resources during common fault condition. Staying connected allows DERs to inject reactive power and stabilize the grid voltage faster after a fault, that we just discussed about it. So, fault write through becomes essential for weak grids, microgrids and future high renewable energy systems, because whenever you have a weak grid, that is already the voltage level, it is not able to maintain its voltage, okay? Or if you have a microgrid. So, at the point of common coupling, that voltage must be maintained to restore the service or to cope up with the faulted condition. So, at that time if you have a DER, so which can locally supply you reactive power or boost your voltage, so that will be a helpful condition. Okay. So, typical FRT requirements or the grid codes, DR must ride through voltage dips down to 0.15 per unit for at least 150 milliseconds. So, that is your standard, that if the under voltage because of the fault, if the voltage gets to only 0.15 per unit, still you can operate or you can stay connected with the DERs for 150 milliseconds, and within that time your system has to be removed from the faulted condition. If it is not, then obviously your DER must be disconnected, but it remain connected till 150 milliseconds. So, maximum reactive current must be injected during under voltage events to help grid recovery. So, you will supply the Q max. We have seen the curve, like the power capability curve of the inverters. So, the Q max we have determined. So, then it will supply the entire Q max, because your voltage is at the lowest level. So, at that time you will give your maximum supply. Disconnection is only allowed if voltage drops below critical threshold for longer than the defined time limits, that is it is more than 150 millisecond. Reconnection to the grid must follow voltage and frequency recovery within the safe operational bands. That means that is the problem. Whenever you will again connect, you have to first check whether your frequency, like your inverter output current or voltage frequency or the voltage level, that is synchronized with your grid or not, or at least within the safe limit. So, that you have to check, and then you can again connect them. Standards like IEEE 1547 or NTSO-E define detailed FRT curves and voltage time requirements. So, these standards are generally followed for carrying out the fault ride through analysis. So, what are the fault ride through methods for DERs? First, you can do the voltage control based FRT methods. What it says? Control strategies in inverters or converters regulate voltage during fault. So, you will keep the, that means you will switching instance, you will regulate for the inverters that the voltages will be at the constant at the output of the inverters. That means the grid following inverters, now you can make it as a grid forming inverters, and then it will give you a supply. Dynamic voltage support, inverters inject reactive current to help the raise the voltage levels, that we just talked. Then you can do volt var control, that means whether your voltage has been reduced. So, at that time you can inject more and more reactive power output based on the local voltage measurements. So, that is normally used for grid tied inverters like PV inverters, wind, your rotor side converter, your grid side converter, that can act as your reactive power support to the main grid, and also you can use the battery storage inverters as well. For specifically for the wind turbines, you have a special arrangement that is called a cow bar protection. It is seen like this. With the rotor circuit, there is a high resistance, it is switched on or switched off depending upon the faulted condition. In doubly-fed induction generator wind turbines, a cow bar circuit protects rotor side converter during faults, because at the stator side, if it is faulted section and it is disconnected, so the fault stator side voltage will start decreasing, okay, but the rotor side will not. That has an adverse effect. The rotor side current will increase, we will see why that will increase, and if that increases, so at that time the rotor will experience a stress condition. So, release that stress, generally at that time this cow bar connection is turned on. So, all the extra current, extra flux will be drained out through this cow bar connection, temporarily bypassing the rotor circuit. Okay. So, you will bypass this converter circuit, allows the turbine to ride through the fault through damaging the converters. So, that will not be damaged through the high currents, and that high current will be diminished or mitigated through this cow bar protection. So, that is specifically for the DFIG wind system. You can have energy storage assisted FRT method, that is the battery or the supercapacitor system provides short term energy supported during faults. So, if you have a voltage dip or you need a support, you just discharge your battery or discharge your supercapacitor. You will get sudden thrust of your power, and then that will boost your voltage level. Supplies or absorbs power to stabilize the voltage and the frequency. Helps to maintain DER operation during transient grid disturbances, and that is mostly used for hybrid DERs, microgrids and utility scale storage plus PV wind setups. You also can provide virtual inertia or synthetic inertia from your inverters. that is a special arrangement we can do, that if the frequency is reduces, that means your system inertia is reduces. So, if that extra inertia needed, you can support from the DER inverters, then your system frequency will again go up and it will stabilize the system. So, inverters are programmed to emulate inertia by releasing energy during frequency dips. So, improves frequency response, helps to prevent system instability in low inertia grid common with high DER penetration. Okay. So, used in advanced inverter based resources including grid forming inverters. So, at that time your inverters will act as a grid forming, now it is giving you the inertia and it is acting as a synchronous generator, and that is why it is called virtual inertia, because it is actually your rotor is not rotating, there is no rotating equipment, but you are getting the output as a synchronous generator inertia. So, what are the challenges for DERs during fault ride through? First, during faults, inverter based and DFIG based DERs experience severe operational challenges including transient overcurrent, control instability and converter stress. So, you are taking the supply or support from the DERs, but the DERs itself experience a very high stress, as we have seen. I have told about the DFIG, your rotor current will become very high. So, rotor is under stress condition. Okay. So, voltage sags trigger rotor overcurrent and DC link overvoltage in DFIG, risking hardware failure unless protected by devices like cowbar, which unfortunately interrupt the reactive power support as well. So, if you cut down this portion and entirely mitigate your overcurrent condition or the high current condition, rotor high current through this cowbar, then what will happen? You are not even getting the Q supply from this grid side converter. So, you are not even getting the supply, or you can say your fault right through operation. It is like just protecting the rotor of the DFIG. It is not supporting the system from coming up, or you can say it is overcome the situation of the fault. Okay. So, fast dynamics in grid impedance and varying fault locations complicate real time detection and control adjustment, making coordinated FRT strategies essential to balance hardware protection and system voltage support. So, what is the voltage ride through voltage sag profile looks like? The voltage sag ride through profile defines clear zones where DR must remain connected during the disturbance. So, if you this is the curve normally followed for ride through operations. So, you see this high voltage ride through lines and this is 0 voltage or low voltage ride through line. So, from there if this is the system, you can see this is your 150 millisecond, what is we have decided that for 1.15 per unit it can run till 150 millisecond. So, if after 150 millisecond if your system voltage again improves and it comes to let us say 0.9 per unit, then this is your connected zone. But if it is not, if it is still remain at the low voltage zone, then you can disconnect it upon agreement. So, this is your operation or the ride through operation of the any DERs. Okay. So, for example, most grid codes specify that DERs must withstand the voltage dips of down 0.15 per unit for at least 150 millisecond. If voltage recovers within the stay connected zone, the DER must continue operation without tripping. So, that means till that point you are connected. After that, if your voltage recovers, then you remain connected. But if it is not at that time, you have to disconnect your DER. Only when voltage drops below critical level or fails to recover within defined time limits are disconnection is permitted. Understanding and respecting this voltage time profile is fundamental to DER controller design, as they guide decisions on ride through versus trip behavior under various faulting scenarios. So, now we will see the behavior of the DFIG wind system during the grid fault condition. When a grid fault occurs, the sudden voltage collapse at a stator terminals of the DFIG machine induces a severe transient. So, stator is directly connected with the grid. So, if any fault occurs, suddenly your stator voltage will collapse or drops. This generates a large rotor overcurrent that can exceed the ratings of the back to back converter. So, that will cause, because of the stator voltage dropped, now your rotor current will increase. So, that current, if you take that current out and send it to the RSC and the GSC, then it will cause overheating, and then your system will completely collapse or it will burnt out. Additionally, the collapse of the stator flux linkage injects large amount of energy into the DC link, causing a dangerous overvoltage condition. Cowbar circuits are typically used to short circuit the rotor temporarily, allowing the converter to ride through the initial transient. Okay? That means, if you connect it, then at the FRT condition, you are stabilizing the operation of the rotor by just mitigating the effect through the cowbar. That means, your extra rotor current will flow through the cowbar and then it will be dissipated as a heat energy. However, the cowbar also forces the DFIG to behave as an induction machine, that means as an induction motor, because now other than generation you are just giving a load. So, that means it will act as an induction motor, disabling its ability to inject reactive power current. Okay. So, how that behavior will look like? The DFIG wind system, when exposed to a symmetrical and an asymmetrical fault, the grid would lead to abrupt change in the stator voltage, and that is given by this equation. When it is t less than equals to 0, at that time this is the voltage. When it is t greater than 0, that means after the fault, this is the voltage. Okay. The stator flux, being state variable, opposes the sudden transition by adding a decaying DC component. So, obviously, any cause that will be in result will be always negated or opposed by the caused. So, if the voltage, if your sudden voltage collapse of your voltage lead to abrupt change in the stator voltage, so that will cause your change in the stator flux as well. So, if the flux changes, so there will be a counter flux that will try to reduce that your changing. So, that is done if that this is your steady state component, then a DC component is added with it. So, this is your DC component and this is your steady state component. Okay. So, during the fault condition, the steady state flux component is stationary with respect to the rotor. So, that respect to the rotor it is stationary. Okay. But thus and induces safe rotor voltage. So, that will not cause any over voltage condition. The over voltage condition occurs due to the transient flux or your DC flux, that is stationary with respect to the stator, because it is a stator flux. So, it is a, and also a DC. So, it is a rotating flux that rotates at synchronous speed relative to the rotor and can induce the high rotor voltage, and that induced over voltage may lead to excessive voltage at the DC link capacitor, potentially causing damage to the capacitor and endangering the system stability. And the EMF induced in the rotor is given by this equation. Okay. This is your actual rotor speed and this is your synchronous speed and the slip. So, to come over from this, generally the fault current limiters are used in the circuit before the DFIG setup. So, what is the purpose of the fault current limiter? Fault current limiter limit fault currents entering to the DR converters. So, it is previous to the DR you place a fault current limiter, and that will limit the fault current moving through the or flowing through the DR connection, but their effectiveness depends upon critically on fault location relative to the DR. So, always the fault current limiter has to be placed before the DR. That means, the fault current should traverse from the fault current limiter and then go to enter to the DR. So, if that is the case, that then only your FCL is good, otherwise that FCL will not operate. So, proper placement downstream enhances the FRT, while upstream faults may worsen the voltage sags due to the added impedance. So, you have to choose wisely where you have to put your fault current limiter. Adaptive FCL control and coordination with DER protection schemes significantly improve system stability during disturbances. So, if we take a case study demonstration with a PHIL setup, that is a power hardware in loop setup, where you have an RTDS, where you will simulate an IEEE 33 bus system, and at a particular bus, that is, let us say bus 5, you have connected physically a DFIG wind setup. So, that your DFIG wind setup will have a, that is run, that DFIG is giving a base frequency, or you can say the wind that is emulated by a DC separately excited DC generator, that will give you that emulation of the wind speed, and then you have an DFIG setup that is connected with a DC motor, separately excited DC motor, and then you have an RSC and GSC control, and that is connected to the bus number 5 through a power amplifier system. Okay, 3-phase power amplifier, and then you put in the RTDS system, you put a fault current limiter before your DFIG setup. So, DFIG is at bus number 5 and your FCL is just after the grid. Okay. So, the system configuration is, the system includes a 33 by 12.66 kV on load tap changer transformer. This is your this one. Then with a plus minus 16 tap positions used to regulate the secondary voltage. You have a primary side of the VLTC is connected to the grid via fault current limiter to reduce the fault current level, achieve relay coordination and improve the fault ride through capability. The wind energy system is a 2.5 kilowatt DC motor having the armature control and a DC-DC chopper. So, DC-DC chopper will give you the proper voltage, and that voltage, that output voltage of that is giving to the DC motor. So, that is the armature voltage you are actually. So, with that, the DC-DC chopper you have, so that DC-DC chopper will give you the armature voltage. So, that armature voltage you can control by giving the motor output, or the motor output means your mechanical output. So, if you control that mechanical output, that is actually emulates the wind speed, and depending upon that your DFIG also speed will be changed, and that will give you the variable wind power scenario. So, the DC motor shaft is mechanically coupled to the rotor of the induction generator. So, this is the overall setup. Again you have a power amplifier to connect the DFIG wind setup with a 15 kV of power amplifier to the actual 33 bus system which is inside the RTDS. So, connect it, you have an ideal transformer method used for communication between the RTDS and the PAS. So, RTD and PAS signal scaling, voltage from bus 5 is scaled by 0.016 times and sent to the PAS. Feedback current from PAS is scaled by a factor of 5 and then returned to the RTDS. So, it is a closed loop system. So, the your signal will go from RTDS through the PAS to the actual DFIG setup, and then again from the DFIG setup the current feedback will go to the PAS and then go to the RTDS. So, there is the system parameters considered for the case study, and then we will do the analysis. With the PHIL experimentation, first we will see without the FCL, that is fault current limiter. So, a 3-phase to ground fault is done at this location, and that is persists for the 100 millisecond duration. Okay. If you see that, then the fault current, this is the fault current that is spiked, okay, that is spiked after initially and then gradually decreases. So, this is your transient. So, after that it decreases. So, that is the actually nature of any fault current. Suddenly it will get a spike, and after some time it will the DC, because of DC offset it will start reducing. Then significant voltage dip is observed at the point of common coupling, that is your this voltage, and your active power at the fault is also energized, and then but your reactive power support suddenly it will drop and then again it will be increased. Now, if you put that fault current limiter, so if you put that fault current limiter and change its ohm values from 0 to 2 ohm, you can see that the initial fault current has been reduced significantly. Okay. You have reduced currents, and from there if you see that ultimately it will settle down to a high value compared to this value, but that initial spike in the current that you can limit with the help of fault current limiter. So, with that help you can get your, you can keep your reactive power supply also constant, and also you are not allowing the DFIG setup to be exposed in front of a very high fault current, at least for a shorter time period, that you are not allowing it. So, you are just maintaining the security of your DER setup, that it can operate smoothly or it can support the system with its reactive power supply. Okay. So, what are the future trends in the fault ride through analysis? Development of intelligent fault ride through controllers using AI based techniques. Obviously, we can go for the faster, if you want faster response we go for AI techniques, but that is a black box model. So, explainable AI we can adopt. Edge AI and FPGA implementation for ultra fast lower latency FRT response during grid faults. Adaptive fault ride through schemes considering grid strength, DER types, protection coordination in real time. Cyber secure FRT solutions to protect the DER controller against malicious fault injection attacks. So, all these considerations we can take when we will see, we will try to minimize the effect of the fault on the DERs, and we can keep the DERs running, keeping considering the standards, that IEEE standards, that it will operate for that 150 millisecond even if the voltage is dipped to 0.15 per unit. So, with this I will end today's lecture and we will continue with our course in the next lecture. Thank you.